we are going to continue our discussions on systems with constraints. We had started discussing problems with constraints and used the method of Lagrange multiplier and derived the equation of motion, equations of motion. And in the last lecture, I had also discussed the interpretation of Lagrange multiplier and how that is used in finding out the constraint forces. In this lecture, I am going to take a few more examples and show you the full power of this method of Lagrange multiplier in determining constraint forces. And remember that in order to determine constraint forces, we have to first break the constraint. Normally, in the method of Lagrange's analytical dynamics, we were not bothered about free body diagrams and internal forces, everything we had bypassed, but in some situations we need to find out certain internal force, and this approach that we are discussing allows us to selectively determine certain constraint forces or certain internal forces. And what is the approach? Approach is that you allow the constraint to be broken, introduce the constraint as a mathematical condition, use the constraint formulation of the Lagrange using the Lagrange multiplier, and find out the Lagrange multiplier and interpret the work done by the constraint forces to determine finally the constraint forces. We will start with this example of a bead on a hoop. The hoop is rotating at a constant angular velocity capital omega. I would like to find out the lateral reaction force on the bead which is on this rotating hoop. What is this lateral force? Lateral force means in this figure, the force that is acting on the bead in the xy plane. Now, this force is acting in the xy plane. Now, that force is actually driving the bead. I also have a top view of this in order to show you how I break the constraint. What do? I consider now these as my physical coordinates. Remember, we have to find out the lateral force. There is also a normal force which is perpendicular to the ring, that we are not interested in, or that we do not want to find out right now. We want to find out the lateral force. Therefore, I must first break the motion of the bead which is constrained to move on the hoop in the way we think about it. What I have done in this figure, where I show the top view, I have allowed the bead to move out of the hoop in the direction, and I call that as phi, that coordinate as phi. I allow the bead to move laterally out of the hoop, and that coordinate, that angle measured from the x axis, which is fixed, actually x y z is a fixed coordinate system, and I measure this plane of the bead by this angle phi. Therefore, the bead has moved out of the hoop. I have broken that constraint, lateral constraint, which makes the bead always stick to the hoop or move with the hoop, slide on the hoop. It can now move out of the plane of the hoop, and this angle I am saying as phi. So, therefore, I am giving an angular displacement, additional angular displacement, which I put as a coordinate. And what is my constraint? Constraint must be phi minus omega t must be 0. Omega, capital omega, is a constant angular speed of the hoop. This angle phi, therefore, must be omega t. If it is not omega t, that means it has moved out of the hoop. Therefore, I first break the constraint, allow the bead to move out of the hoop in that angular direction, and call that phi as a new coordinate, and now mathematically introduce this constraint phi must be equal to omega t. We write down the Lagrangian as usual, but now we have contributions from that phi coordinate as well. This we must keep in mind. Kinetic energy is half times mass times velocity of the mass whole square. Now, I have to find out that velocity of the mass. First, I start from the position vector of that mass point in the coordinate system shown. This is straightforward to write. Here, rather than phi is equals to omega t, I have introduced this phi, right. Now, that gives the bead a freedom to move in the phi coordinate direction. Now, phi is not omega t. Remember that when we were considering the constraint system, we were taking in place of phi, we were writing omega t, but now I allow it to be broken. So, I have written a general phi, it is a coordinate for us. We will introduce the constraint that phi must be restrained as omega t. We will do that. Now, velocity I can find out. So, this is the velocity. Now, phi gets derivated as usual. I have expressions of phi dot in my velocity, and therefore, velocity of the mass whole square is this expression r square theta dot square plus r square phi dot square sin square theta. This is the velocity square, and therefore, now I have the kinetic energy with me. Potential energy is as usual, because phi does not change the potential energy of the system. Phi does not change the potential energy of the system, but theta does. Therefore, we have only theta dependence. We have the Lagrangian now. We start with this Lagrangian and the constraint. Our governing equations, we have derived this general form of our governing equations. We have two coordinates, therefore, two equations corresponding to each. First equation is corresponding to phi, second is to theta, and additionally we have this constraint. We have three equations in three unknowns, phi, theta and lambda. We will start one by one with the phi coordinate first. We find out this del L del phi dot and d dt of that. Del L del phi is 0. You can see that the Lagrangian is not dependent on phi explicitly, and del C del phi, the derivative of the partial derivative of the constraint with respect to phi is 1. The constraint is written out there at the top, and you can very easily check this del C del phi is 1. Therefore, the equation of motion corresponding to the phi coordinate is given like this. I leave the details to you to fill out. Then we move over to the theta equation. We again determine these terms del L del theta dot and d dt of del L del theta dot. In this case, they are straightforward. Del L del theta, we have contribution from theta in the Lagrangian, and these are our this is our expression for del L del theta, and del C del theta is 0. We do not have any theta dependence on in the constraint. Therefore, equation of motion in the theta coordinate direction is this, which we can simplify a little bit more to get it closer to the pendulum equation. There is an additional term, of course, the second term. Okay. So, what do we have? We have the equation of motion corresponding to the phi coordinate, which is the first equation and which also involves the Lagrange multiplier. Second equation is the equation of motion corresponding to the theta coordinate, and finally, we have the constraint. We follow our usual steps. We start derivating the constraint and using it in the equation of motion, finally to solve lambda. Our main goal is to solve lambda. Therefore, substituting this expression of phi and theta double dot in the first equation, so we can find out phi double dot, etc. Phi double dot is actually 0. If you see this phi double dot is 0, phi dot is omega. And theta double dot is obtained from the second equation. All those things I will substitute in my first equation. Phi double dot of course is 0, rest of it gives me lambda directly. Now, we have to interpret this lambda. Work done by the constraint force is given by lambda delta c. This is our term in the in our statement, a variational statement, from where we derive the equation of motion. This is the work done, this has dimensions of work or energy lambda delta c, and that must be equal to the generalized constraint forces dot the corresponding variation of the coordinates. When we talk about the generalized force in the phi direction, generalized constraint force in the phi direction, it must be multiplied by delta phi, the variation, to give the virtual work done by in this coordinate direction. Similarly, delta c theta is the generalized constraint force in the theta direction, in the theta coordinate direction, that must be multiplied by the variation of the theta to give us virtual work done by the constraint force in the theta direction. And if you look at this expression of if you look at this expression, then you can note that this constraint force in the theta direction must be 0. If you for that you will have to look back and see that term lambda delta c. Lambda delta c is nothing but, from here delta c I can find out lambda delta phi. Remember that delta does not derivate time, therefore, it is delta c is only delta phi and lambda delta phi. In other words, we do not have any delta theta contribution, that is to say that the constraint for generalized constraint force corresponding to the theta direction must be 0. And if I look at, if I interpret what is the work done, who does this work on the bead, if I ask this question, because you see this delta phi, phi is an angular coordinate, phi is an angular coordinate, delta phi is an angle, variation in the angle phi. Therefore, the corresponding generalized force must be a moment. That is what I have written, moment of the lateral force about the axis of rotation. This, how is this moment being produced? It is the moment about the axis around which theta is being measured, about which theta is being measured, which is the z axis, which is our z axis. We want to find out the force, lateral force, remember. Now, this lateral force produces a moment about the z axis, and how do I find that? I multiply this f by this radial arm, and this, how much is this radial arm? This radial arm. Now, that must be this radius of the hoop times sin theta, radius of the hoop times sin theta. It is like this, that this is our hoop, this is our bead, this is our angle theta. Therefore, this distance must be r sin theta. Once we have understood that, let us proceed. Therefore, lateral force produces that moment is nothing but the force, lateral force times the moment arm, r sin theta, and that must be equal to, as you can see from here, this moment is nothing but our Lagrange multiplier. Moment is Lagrange multiplier now is a moment. Lagrange multiplier here has a dimensions of moment. Now, how do I find out force from here? From this condition I can find out the lateral force, and how much is that? It is 2 m r omega theta dot cosine theta. This is our lateral force. Now, here in this example I want to point out once again the Lagrange multiplier has dimensions of moment, and the force it has dimensions of moment because the corresponding coordinate is an angular coordinate. What gives me the work by the constraint force? So, if it is if the angle if the coordinate is an angular coordinate, then the corresponding generalized constraint force must be a moment, and from there we found out the lateral force. Therefore, we have our equation of motion, only theta is our coordinate actually. Remember that we have derived this equation of motion for the hoop on the rotating for the bead on the rotating hoop. This is our equation of motion, and now in addition we have also found out the lateral force. You can also find out the radial force, and that I will leave to you. How you break the constraint? You have to break the radial constraint to find out the radial force. Now, we come to this rolling disc on an incline in a uniform gravitational field. We want to find out that friction force at the contact. When we derive the equation of motion for such a system using the analytical mechanics approach, we never worried about the constraint forces, never worried about any internal forces. But now we are going to selectively determine the friction force at the contact. So, how do I do that? I must break the constraint that generates the friction force, or looked at in another way, I must allow that friction force to do some work, some virtual work. That is the same thing as saying I must break the no slip condition. I must break that no slip condition. How do I do that? I must take x and theta both as coordinates. How is x measured? I have drawn the coordinate system x y, which is aligned, x axis is aligned with the inclined plane, and I have also shown the datum which we will require for the potential energy calculation. I have considered this x and theta both. Remember, when we have pure rolling, x and theta are dependent, but now I break that dependence. I allow the constraint, rolling constraint, to be broken, thereby allowing the friction force or the constraint force to do some work, virtual work, not real work. Our constraint is x minus r theta equal to 0. This is our rolling condition, rolling without slipping. But we take the coordinates x and theta, that means we are breaking, as if we are breaking the constraint and introducing the pure rolling constraint by this mathematical statement, which we call constraint, and introduce it in our formulation. Lagrangian, we have to write down the kinetic energy and potential energy. Now, the kinetic energy expressions will have this effect of breaking the constraint. It is no longer simply the rotational kinetic energy that we have looked at previously or use the constraint for. We must write half m x dot square plus half I theta dot square, which means the kinetic energy of translation plus the kinetic energy translation of the center of mass plus the kinetic energy of rotation about the center of mass. Both of them are now kind of independent because we have broken the constraint. Potential energy is as usual, it only involves x, and the datum is shown in the figure. From there we have written the potential energy expression, and the Lagrangian is shown here, kinetic energy minus the potential energy. Therefore, we have this Lagrangian and the constraint, rolling constraint. Our governing equations, this we have derived and used many times. These are our governing equations of motion corresponding to the x coordinate and theta coordinate, and with that I also have the rolling constraint, x minus r theta is 0. We have these 3 equations involving 3 unknowns x, theta and lambda. We will look at it one by one. The x coordinate first, del L del x dot, straightforward, d dt of that is simple, del L del x, and del c del x is 1. The constraint is written out there at the top. You can check that del c del x is 1. Therefore, equation of motion, just we plug in these expressions in the equation of motion and we obtain this as the equation of motion corresponding to the x coordinate. Similarly, for the theta coordinate, I calculate these derivatives, del L del theta dot and d dt of that. These are straightforward calculations. There is no dependence of the Lagrangian on theta, which is the rotation of the disk. Now, del c del theta is minus r. Once again the constraint is written out for you. You can check that del c del theta is minus r. We plug in all these expressions in the equation of motion and this is what I obtain, I theta double dot plus r lambda is equal to 0. What all do we have now in our hand? We have the equation of motion corresponding to the x coordinate, the first equation. The second equation is the equation of motion corresponding to the theta coordinate, and we have the constraint. We solve for the Lagrange multiplier. As usual, we start derivating the constraint, use the equations of motion and solve for lambda, and that this is what we obtain as lambda. This is our Lagrange multiplier. We have to interpret or we have to find out, remember what we have to find out? We have to find out the friction force, the force at the constraint which maintains this rolling condition. We have to find out that force. We start looking at the work done by the constraint forces. Remember that lambda delta c has dimensions of energy or work, and if you write down what is lambda delta c you can easily write it is delta x minus r delta theta. So, lambda delta c is this, and that must be equal to, in terms of our generalized constraint forces, must be equal to the generalized constraint forces in the x direction delta x, which is the work done by that generalized force, and the generalized constraint force in the theta direction times delta theta, which is the virtual work done by the force component corresponding to the theta direction. And now I compare and find out what are these forces, and now we have to also look at which is that force which is maintaining this rolling condition. This is the friction force. I have drawn the constraint force diagram. This is not a free body diagram, this is the constraint force diagram. I have only shown the constraint force which we are interested in finding out, which is this friction force F, and therefore I have another interpretation how I find out the work done by this force, this constraint force. How do I find out the work done by this constraint force? I find out what is the virtual displacement. I want to find out the virtual work done by this constraint force. What do? I have two coordinates and I take variations. If I give a small displacement, variational displacement, so delta x in my x coordinate direction, what will be the work done? Notice we have to take dot product of the constraint force vector and the variational displacement vector. Look at these two directions, they are in opposition. Therefore, the work done must be minus f delta x, that dot product. Never lose track of work done as a dot product. This you have to remember, otherwise everything will go wrong. The work done by the constraint force when I give a variational displacement delta x is minus f delta x. That minus comes because of the dot product. Work done is a dot product between force and virtual displacement, that is virtual work. Okay. The other coordinate is delta theta, the variation in the other coordinate is delta theta. This, and this is the direction we have considered throughout. What will be the work done by this force F corresponding to this variation delta theta? Remember, F is a force, whereas delta theta is an angular displacement. Therefore, to have dimensions of work, I must have moment because of this force. How do I find out moment? I take the arm, find out the moment. So, r times F delta theta, and now you note that the moment and the variational displacement delta theta are in the same direction. Therefore, the work done must be, and that must be the complete work done, virtual work done by the constraint forces. Now, that is what I am going to use, minus f delta x plus r f delta theta, from where I can actually interpret. What do I interpret? What do I interpret from here? That my constraint force, that friction force F, must be minus lambda. Here lambda has the dimensions of force. F must be equal to minus lambda, and lambda's expression we know. So, this was our friction force, the constraint force. To summarize, we have looked at systems with constraints. We introduced the method of Lagrange multipliers to determine the equations of motion. We have interpreted the Lagrange multipliers and seen how they can be used to determine the constraint forces. Once again, to recapitulate, what do we do to find out, to selectively find out certain internal force or constraint force? We break the constraint, we introduce additional coordinates which imply breaking of certain constraint, which force I want to find out. We break that constraint by introducing coordinates, and this we can do selectively, unlike in Newton's approach. Then we allow this constraint forces to do work, we find out Lagrange multiplier and write down the force the virtual work done by the constraint forces, interpret it in terms of the internal force that we have in the system, and finally obtain the internal force, and that is found to be proportional to the corresponding Lagrange multiplier. With that, I will conclude this lecture.